So today we're going to start with we're going to talk about electronic excited states. So going from what Tony's talked about in the past 2 days, mainly single determinant wave functions, to what, well, first of all, why don't single determinant wave functions describe electronic excited states? Well, but first we'll start about why we care about electronic states, and then how we're going to excited states, and then how we're going to deal with them. And hopefully all that, the sort of theory side of it, the presentation side of it, will be relatively short, and then we'll work with Gauss-U to set up some calculations on benzene, and then your project will be to do the same thing for naphthalene and anthracene. Okay, so there's some files available. I just put them up today that will allow you to follow along in class with Gauss-U for the ethylene and benzene examples I will go through. But if you don't have Gauss-U on your computers, I'll just be projecting them up here, so it doesn't really matter. Okay. All right, so electronic excited states of atoms and molecules. What is an electronic excited state? So this is a picture, some various pictures of, on the bottom right are pictures of hydrogen-like orbitals. And on the sort of top right and bottom left are two different depictions of the, sorry, this is being annoying. Tony, is it looking fine on yours?
Yeah.
That's weird. Okay. I have to do it 3 times. Okay, anyways. Doesn't look fine. And then the bottom left, top right are depictions of the hydrogen spectrum. So who knows what an electronic excited state of an atom or molecule is? That's a good description of that. First.
When an electron absorbs, goes to the next quantum level.
Good.
So it absorbs a certain amount, like an exact amount of energy.
Quantized, right, yes, exactly. Perfect, yes. Okay, so an atom or molecule is sitting in its ground electronic state. That we've talked about how to characterize that, how to solve for the wave function in the past couple of days, and how to get that information. And now it gets hit with some energy, and that pops an electron. If it's exactly, as Matthew said, an exact amount of energy, meaning if it is exactly equal to a delta E within the orbital or state diagram of your electronic states of your atom or molecule, then you will excite to that. You will excite one electron or an electron, a set of electrons to the excited state. Okay. So within the hydrogen spectrum, there's a whole bunch of these transitions that go from, for example, if you go to the first excited state, that's taking your 1s electron to a 2s state. Okay? So n equals 1, n equals 2 here, so you're going from this, an electron occupying this red orbital, the bottom left, to this blue orbital, 1 over. Okay, and then if you want to excite it further, you would be going into 2p orbitals, eventually 3s, and so on and so forth. So another way of depicting, so why do we care? I forgot about that part of it. What is an electron state, and why do we care? Well, it happens all the time. For example, dyes. Here's a few examples. PDI is actually what we work on in my group. Not the excited state properties of it exactly, on aggregation properties, but chromophore-like molecules absorb energy and have a color associated with them. Because of that, they're absorbing in the visible and have color associated with that, or emitting actually. Biology is also photosystems, for example, absorb energy from light and excite electrons to excited states, and actually, and then those excited states move around and transfer energy. Energy materials such as PDI also exciting an electron hole pair and having that electron hole pair actually separate and then transport through a material is a way to get charge transport, and ultimately, for example, in photovoltaics, a very important process in that. Okay, so it's an important thing to think about, and so let's get back to the hydrogen example. So what I sort of described previously is that you have an electron in the 1s in the hydrogen ground state, excited to the 2s. Okay, so you get some sort of light or energy that is resonant with that transition, and you excite from the 1s to the 2s. And you go to the 2p and so on and so forth up to the dissociate until you eventually ionize your molecule. That electron, at some point, those energy spacings become closer and closer together until they basically become a continuum, and then you dissociate the electron from the hydrogen atom in this case. Okay, so hydrogen is a relatively simple picture because we have only one electron. What happens when we have multiple electrons? So the simplest example for that is helium. So in helium, the story is a little bit more complicated because you can say you shine light that's resonant with the 1s to 2s transition. You excite one of these electrons from the 1s to the 2s. But what's the problem with that picture? Does anyone know? So which electron, I mean, I picked one electron here. I said this electron goes from the 1s to the 2s. Is that, the energy is simply resonant with that transition. Is there another option that you can think of that would satisfy that? Yeah, Troy.
The electron that's on the left or the whatever, they show by the arrow facing up. That could be the one that
Right.
was moved up to the excited state.
Sure. Are there any other options that could, yeah?
The one that, let's say if you move the one on the right, like let your change the spin.
Good.
What do you do?
Good point. Right. So what happens with the spin? I've decided what I've represented here would be a singlet going to a singlet. That's not necessarily the case. You could have a spin flip and get a triplet. So yeah. Oh, H nu. It's just energy of the light that's, oh, I see, you're shooting. So it's just energy, basically. It is HV. I didn't put a nu there, actually. Okay, so this brings us to, so there's a relatively complicated picture here of how do we actually describe that. So we're going to describe that using wave functions. I'm going to start with the spatial part, but then there's also the spin part. So the spatial part is which electrons are in which orbitals. Okay, and what I had on the previous slide is something like this. One of the electrons is in the 1s, one of them is in the 2s. But of course, you could flip which electron is there, and you get the flipped version of that. Unfortunately, this description does not satisfy the Pauli principle, which states that the overall wave function, including the spatial and the spin part, must be antisymmetric with change of electron. So you actually have to do a linear combination of these two wave function type things to actually get the real spatial components of the wave function, where you get now a symmetric and an antisymmetric version, where the symmetric version is just a positive linear combination, if you will. The antisymmetric is the difference between it. Okay, any questions on that? So this is just the spatial component. We have to talk about the spin component now. Okay, oh, sorry, this depiction sort of what the spatial component represents. So we no longer have spin associated with these electrons. That's why they're now just solid lines. But the symmetric guy is an addition of these two components, and the antisymmetric is the difference between those two components depicted spatially. Okay, now for spin, and much like in the spatial component, spatial part of the wave function, we have a symmetric and an antisymmetric. version. And alpha is just representing, let's say, up. Alpha is representing an upspin, and beta is representing a downspin in this case. Whatever, doesn't matter as long as it's a binary thing. So we have a symmetric, we have three different symmetric versions of the spin wave function, alpha, 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 beta, plus beta, alpha, and beta, beta. Okay, and you can see that they're symmetric by just flipping alpha and beta and seeing if they're equivalent. Then we have an anti-symmetric version of the spin part of the wave function, alpha, beta, minus beta, alpha. Okay, so now the total wave function for the system is the product of the spatial component times the spin component, but we can only, the overall wave function must maintain the Pauli principle, must be anti-symmetric with changing the spins, so you can only multiply the symmetric component of the spin by the anti-symmetric component of the spatial, and vice versa. What that yields is 4 different wave functions, 3 that are triplet, meaning the spin is a triplet spin, and 1 that is a singlet. So this is the symmetric spatial component multiplied by the anti-symmetric spin component, and this is the anti-symmetric spatial component multiplied by the 3 different symmetric spin components of the wave function. Okay, does any questions on that? So ultimately, I mean, what does this all mean? Well, it means that in order to describe, even in the helium, fairly simplistic helium case, the first excitation, we need 4 different wave functions. Okay, so a single wave function that we describe the ground state with is no longer satisfactory in these cases. So we need something that's more complicated to deal with this. Typically, we call them multi-determinant, but there's also a time-dependent formalism, which is a bit different and out of the scope of what we're going to talk about today. But it's very starting about 10 years ago or so, became very popular TD-DFT methods to compute a ridiculous number of excited states using relatively minimal computational costs. But the multi-determinant methods like configuration interaction and its variants, including sort of CAS-SCF, and a couple of cluster methods are where you write out a variety of determinants for your system and then you combine them in some fashion. Configuration interaction and CAS-SCF is what we're going to focus on today. So configuration interaction variants include configuration interaction singles and configuration interaction singles and doubles and so on and so forth. And then also CAS-SCF is a variant on CI as well. Okay, so what is CI? What is the configuration interaction? So what we do is we describe the overall wave function as a sum of single determinant, usually, wave functions times some coefficient. So these single determinant wave functions in this equation are much like what you've already determined or what you were computing in the previous few days. But now, instead of just having one of those, we have multiple of those, and then we use a variational principle to compute the CIs that optimize the Schrodinger equation. Okay, so what does configuration interaction do? What is the procedure? So try to avoid math. Let's just think about the procedure here. The first thing they do is to determine the linear combination of atomic orbitals lead to a variationally called molecular orbitals, and the coefficients of those are determined using the single configuration SCF, such as partial product GFT that you've used so far. And then you optimize your CIs based using so the CIs, meaning those coefficients of the previous equation, are optimized in a variation principle for a given root, meaning I want the first root of this equation or the ground state, the second root, first excited state, third root, second excited state, and so on and so forth. And what you basically do is you take all your initial ground state electron configuration, and then you allow for every single possible excitation, including taking every electron and putting it in every single unoccupied orbital, and then computing the coefficient of that part of the wave function. And then you do it for doubles. So now instead of just exciting one electron, I excite multiple electrons. Okay, and that's another one of these phi i's in the previous equation. And so this procedure becomes very computationally demanding. In particular, it scales as 2 to the x, where x is number of electron pairs, basically. Okay, so that becomes very, very computationally. So there are reduced ways, so there are computationally less demanding ways of solving this, including CAST-SCF, which stands for complete active space substance. And that's what we're going to focus on today, and that's what we're going to work on for the project, the method that we're going to utilize for the project. Okay, so we're going to go into how to set up these calculations and how to actually do them, but before we do that, we have to talk a little bit about molecular orbital theory. Who has heard of molecular orbital theory? Okay, so who can tell me something about molecular orbital theory? Yeah.
It's like a picture of all the orbitals, possible orbitals, ranking from like lowest to highest energy.
In a molecule, right, perfect. Okay, good. So how do I determine how many possible orbitals there are in my molecule?
The number of atomic orbitals.
Okay, and then how do you relate those two? Are they equivalent or equivalent? Okay, so this is an example where I have two atoms coming together to make, let's say, hydrogen coming to make H2. Okay, so my molecule is H2, the comprising atoms are hydrogen. So hydrogen, in its atomic state, has a 1s electron. The other hydrogen has also 1s electron. So 1 electron each, and they're both in the 1s orbital. This creates 2 molecular orbitals, much as Rebecca said. Does anyone know what this picture is showing here? What kind of orbital that is? Good, it's a bonding orbital, in particular a sigma bonding orbital. What about this one?
Sigma antibonding.
Antibonding, perfect. Okay. So what happens is you combine these 2 1s orbitals and you create 2 molecular orbitals, but you also split them. That's very important. One becomes lower in energy than the 2 independent in this bonding orbital, and one becomes higher in energy than the 2 independent in this antibonding orbital. Okay, any questions on that? All right, so that was hydrogen relative to the picture. Now we're going to do something a little bit more complicated. It includes a double bond. That's going to be important for benzene to understand what that is. And that's ethylene. Okay, and I just took this picture from the web, and this is supposed to represent the atomic orbitals of the comprising atoms, and then this is molecular orbitals. Okay, so we have 4 hydrogens, each with 1s orbitals occupied, and then we have 2 carbon atoms with 3 hybridized orbitals being occupied. Hybridized orbital being occupied, but it doesn't matter. We're contributing 4 orbitals from our carbon, which results in this picture anyways, 1, 2, 3, 4, 5, 6 sigma bonding orbitals, 1 pi bonding orbital, 1 pi star. So pi star represents antibonding, and then 5 sigma star antibonding orbitals. So we're going to take a look at this in Gaussian. Okay, so if you have downloaded these files, you can follow along on your own computer if you have GaussView. But I'm in the ethylene, so you should have something that looks like this if you're following along. And I'm going to go into the ethylene folder, and you should see the following files and folders. And I'm going to look at the check. So what I have done is I have run a density functional theory, geometry optimization of ethylene. And we're going to look at the orbital output in the checkpoint file. Okay, so I'm just launching Gaussian like this. However you want to launch, it's fine. And we should get a molecule that hopefully looks like ethylene. Okay. Actually, this one is big. And so we're going to look at the molecular orbitals using the edit MOs function in Gaussian, or Gaussian, sorry. You should get something that looks like this when you do that. I'm going to expand this window a little bit. Okay, if everyone's following along, we're going to go to visualize now. So here are the orbitals. Yeah.
Sorry, but how'd you get to that window, the bottom show?
Edit, what, this window here?
No, where the bottom that you have open.
Well, this window is part of the bottom, right? I mean, so this, I don't know, they're all attached. So I want to edit MOs when I have the checkpoint file loaded. Okay. So what you're going to see in this window is, well, besides the molecule, on the right-hand side, we see a list that goes from 1 to 38 in this case. And these are representing the orbitals and the occupations of them. And so in orbital 1, we see it has a negative 10.17 energy or whatever, but we can also see these little up and down arrows, red arrows in there, denoting that this is a doubly occupied orbital. And that goes all the way up to the highlighted orbitals, which 9 is the LUMO, lowest unoccupied molecular orbital, and 8 is the HOMO, or highest occupied molecular orbital. And then there's this green line in between representing the separation between the two. So we want to visualize pretty much all of these orbitals, and so I'm going to, not all the way up to 38, but I want to add a list of 1 through, let's say, 12. And then I hit update. It's going to take a little second because you guys probably saw this before where you were doing cube representations in that other window, but they have to compute those three-dimensional representations of all of these things. So it takes a little second, but once it does, it should load all of them. And now you'll see a little red or squares next to the ones that you asked to visualize. And right now, the one that is red is orbital 12. And so that's what we're visualizing here. I will also point out that if we went back to this PowerPoint file, we were looking here at 1, 2, 3, 4, 5, 6 occupied orbitals here, right? Does everyone agree with me that that's 6 over there? Now, if we go back to Gauss view, how many occupied orbitals are there here? 8, okay. Can't read, it's too small. It's 8. What does anyone know why there's a discrepancy there? Six versus 8 is the discrepancy. Yeah.
Does it have to do with the double bond?
No, actually, it has to do with the fact that I didn't mention that this is only the valence electrons. Okay, so there are core electrons in carbon. So carbon comes together, makes a double bond, right? One of which is a sigma bond. Sorry, but that's going to. But there's also 1s orbitals on the carbon that are in the core. So there's the valence electrons, so the 2s and the 2p. So the core 1s orbitals still come together and make. So you have 2 of those, right? 1 from each carbon. So that's going to make 2 corresponding molecular orbitals as well that are not counted for in this diagram here. So that's why you see in the Gauss view picture 8. And we should see that by clicking, we can see that by clicking here and looking at the picture of what this orbital represents, okay? So now we see these red spheres-like things surrounding the carbon, representing electron density around each of the carbons that is not in the middle, not forming a sigma bond, okay? And this is the completely symmetric case in the lowest energy orbital. And now we're going to have an anti-symmetric 1s carbon 1s molecular orbital as our second orbital, okay? And the other 6 are corresponding to what we saw on that PowerPoint slide. Any questions on that? Okay. So now let's just work our way up the other 6 and let's talk about what they are. Okay, so now what is this? Does anyone, besides a red sort of blob, does anyone have an idea of what kind of an orbital that is? Okay, what about this one? What about this one? Yeah.
The first one, like an S orbital, and these are like the other ones like PX, PY.
So there's no longer PX, PY. That's atomic orbitals, right? These are molecular orbitals. So there's some sort of combination. So this is the completely symmetric sigma bonding orbital, and it has both carbon-carbon sigma bond nature and carbon-hydrogen sigma bond nature in there. And you'll sort of notice that in this case also the completely symmetric version of the 1s orbital was the lowest energy. Now the completely symmetric sigma bonding orbital is the lowest energy. So that just notice a little bit of a trend there. This is a carbon-hydrogen sigma bond orbital. This is another carbon-hydrogen sigma bond orbital. Now, what about this one? Yeah.
It's the antibonding.
No. It's still occupied, right? It's number 6. And if we look at this diagram, only bonding orbitals should be occupied.
Another sigma bond.
Is another sigma bond, right? So go back to this PowerPoint slide. You can count how many sigma bond orbitals should there be. 5. Okay, so we're working our way up. Again, sigma bond, carbon, hydrogen. Okay, this doesn't have any carbon-carbon sigma bond nature. Okay, what about this one? Good. This is our pi bond. Okay. And so those are all of our occupied orbitals, and so that agrees reasonably well with what we had here. Additionally, notice in this PowerPoint slide that energy is on the y-axis here, so there should be significant discrepancy in the energies of the sigma bond orbitals and the pi bond orbital. And you should be able to look at that based on estimate that based on the energies of these orbitals here. And there is some difference. But I can't see, the numbers are even small on my thing, so I'm not going to compute it. But it's actually maybe not as drastic as is sort of displayed on that graph. Okay, so now we're going to look at some anti-bonding orbitals. Now what is this one? Pi star, good. This is a weird looking one, but is a sigma star orbital. Okay, so why am I doing all of this? Well, we're going to, for this is, I mean, you can see how somewhat challenging it is to sort of pick out what the nature of these things are, and it just takes experience in looking at them. But we're going to do it for benzene, and you're going to see so we're going to do it for benzene, and you're going to see in a second. We're going to try to create a particular CAS, complete active space, of certain orbitals, in particular the pi and pi star orbitals. And so we're going to have to look at the orbitals and figure out which one are pi and pi star. Because that we're going to have to tell the program we want these orbitals to be in our active space. So we have to tell it exactly which ones. Okay, so let's just quit Gaussian now. Go back to this. All right, so we looked at that and we saw that there are actually 8 orbitals, 2 of which were 1s, carbon 1s orbitals. Okay, so, oh man, it's weird, isn't it? Okay, for molecular electronic excitation, the process is very similar to atomic electronic excitation, where we start with our ground state electronic configuration, and then we excite one electron potentially into a different orbit. Okay, so this is not quite the ethylene case. The ethylene case would be much more like this, with a bunch of other electrons, and then we simply excite from pi to pi star. And that's the main excitation we're going to look at today and in the project. So what does complete active space self-consistent yield? Well, instead of looking at all possible excitations of all of the electrons, so here, for example, this is sort of similar to the picture of ethylene, all of those occupied orbitals, here's all of our unoccupied orbitals. What full CI would do is look at all possible excitations, including all single excitations, taking every single electron, moving it there, putting it back, and then doing another one, so on and so forth. All double excitations, all triple excitations, so on and so forth. And that becomes computationally intractable beyond some very limited subset of molecules. So what complete active space does is takes a small subset of our occupied and unoccupied orbitals and said, we're going to look at a full CI, so allowing all possible excitations, but only within this subset. This is only, so, which works actually pretty well for things that, for not surprisingly, excitations that only happen from and within this space. So typically for situations much like in pi systems where the pi orbitals have large energy separations from the sigma orbitals. So the first few excited states are likely just taking the pi electron, one or the other, and putting it into pi star state. So if I only want to look at those select excitations, I can just say, don't worry about taking something from the carbon 1s orbital and putting it into the pi star orbital, because that's going to be humongous in energy, not going to contribute to the wave function of my first excited state. So I don't need to worry about that. So I just say, okay, look at all excitations in this space. So for all of the systems we're going to look at, this is going to be the pi star CAS space. For ethylene, how many orbitals does that contain? Yes. 2. How many electrons? 2. Okay, so the pi star CAS space in ethylene would be denoted 2-2. 2 electrons and 2 orbitals. So you say this is CAS SCF 2-2 for ethylene. Okay, so you'll see on this thing, I tell you what it should be for naphthalene, but for benzene, for example, it's going to be 6 electrons and 6 orbitals. The ground state, the 6 electrons in that, and so this would be a good example of what the benzene system will look like. The ground state, the 6 electrons are occupying 3 orbitals, so then you have 3 pi star orbitals to which you can excite the electrons.
Are those always going to be degenerate, or are they just like like for 6-6? Is it like the 3 like lowest unoccupied and the 3 highest occupied? So is it just go to take those?
No. So we're going to go through that. So, but we specifically want the space to be the pi star space. In ethylene, if we just said CAS SCF 2-2 of the wave function that we just looked at, of the orbitals from the wave function we just looked at, then it would be right, because those are the highest occupied and lowest unoccupied orbitals, so everything would be fine. What we're going to see in the case of benzene, and actually Tony mentioned it yesterday, I think, that's not always the case. So polyenes, you can do the same thing. We're not going to go through that, actually. I'll skip through that. Okay, so benzene, so now we're going to look at how to do this for benzene, and this is going to feed into your project. So the workflow to perform CAS SCF calculations is as follows. First, we got to pick the molecule. Then you got to optimize the geometry of the molecule. In this case, we're going to use DFT. Okay, that's going to give us the optimized geometry as well as the wave function, the starting wave function for our CAS calculation. So we need not only the geometry, but we need that checkpoint file. That's going to be the start of our CAS. We're going to use that in our CAS calculations. Once that's done, you look at the orbitals and determine the active space. So this is getting to Ellery's question. We're going to go through that. And then you set up CAS calculations, which in the case of anything that requires you to swap orbitals out, which we'll go through, you first have to run a CAS calculation to swap the orbitals, and then you run a second CAS calculation. A given route, which we'll go through and rinse and repeat. Okay, for all possible routes. A route is, I want the first excited state, I want the second, that would be the first route. Sorry, the ground state would be the first route of your CAS wave function, and the first excited state would be the second route, so on and so forth. Okay, so now let's go back to terminal, and we're going to go into, if you go into the benzene folder that I gave you guys, you should see a bunch of files, okay? This is basically that workflow in a single folder. You can break it up however you want, however you like to be organized. But for now, I'm going to actually just show you how to set up all of these calculations from the beginning. I'm not necessarily going to run them. You can run them on the cluster like you've been running before, but I'll set them up using Gauss view. And then we can go back and look at the output from the files I've already run. So make a directory, benzene new, for example. Go into this folder, there's nothing in there. Gauss view. Okay, and then you just create benzene. Calculate, calculation setup. We're going to first optimize. Remember, that's the first part. Minimize, never, blah, blah, blah. Ground state, DFT, default spin, V3 lit. I'm going to use the 6311G basis set, and that's pretty much it. Okay, so you hit submit, save. Save your Gaussian input file and don't run it locally, and that's it, okay? And then you take that file and you go run it on the cluster. Or you can run it on your own computer. It should not take very long. It's running now on this laptop. Meanwhile, we can go back to Gauss view. Create benzene again. Oops, that was 2. Get rid of that. Energy, method. CAS SCF, 631G star. We want to do a 6.6. I don't know why that's not letting me change that to 6. Now I'm just using this to set up a file which I'm going to alter, okay? But this is a way that you can just at least get the keywords that Gaussian requires in that little line to run a CAS SCF calculation. So I'm going to call it benzene CAS-SCF66.com. Cancel. Okay. You can see how your job is doing. Apparently it's already done. Okay, so our optimization job is already done. I ran it on my laptop here and it's already done. Okay, it's fast. So now we're going to view the benzene optimized, B3-lip optimized checkpoint file. And do the same thing we did for ethylene, go through those orbitals and look at them, okay? And if you have Gaussian, you want to follow along with those files in the folder that I uploaded. The file names are the same, so you can just load that benzene B3-lip opt.check in there. Oh, we got to highlight this window, and then we edit the molecular orbitals. We should get a window that looks like this. Okay, and you see something pretty similar to what we saw for ethylene, a whole bunch, but now more occupied orbitals. All of them are doubly occupied, which is good. And then some virtual orbitals on top of that. So now we need to go through, and we should have a notebook or a piece of paper, or I guess you can take notes on your computer. We're going to go through. We should have to go. We could go through all of them. We'll start with the occupied orbitals and look at the nature of these orbitals. What type of orbitals are they? In particular, we want to determine are the lowest. So we think that 19, 20, and 21 should be our pi orbitals, pi bonding orbitals. Then 22, 23, and 24 should be our pi star orbitals. I'm going to tell you right now that's not going to be the case. So we need to figure out where those pi and pi star orbitals are, what their numbers are, so that we can switch them into the 19, 20, 21, 22, 23, and 24 space. So I'm going to go to visualize, and I could start at 1, but I'm not going to. I'll start at 15. I'm going to go all the way up to, let's say, 30, okay? And I'm going to visualize 15 to 30. Update. And this will take a second. When it's done, they should start drawing a bunch of things. Any questions on this so far, what we're doing here? Yeah.
Why are you going above the number of like bonded ones?
Because
They're just only looking for like the 6 pi orbitals.
I want, so there's how many pi bonding orbitals are there in benzene? No, there's 6. So there's 6 p orbitals from the carbons that are contributing to the pi orbitals, right? So there are 6 pi-like orbitals in benzene. How many of them are bonding? 3. So 3 of them should be contained in the occupied orbitals, and 3 of them should be contained in the unoccupied orbitals.
For all 6.
So I need to make sure not only that are the 3 occupied, lowest occupied, or highest occupied molecular orbitals, the HOMO and HOMO -1 and HOMO -2, those have to be pi, but LUMO, LUMO +1, and LUMO +2 must also be pi-like, okay? So that's what I have to determine now. Where are my pi-like orbitals? Are they 19, 20, 21, 22, 23, and 24, or are they elsewhere? And do I have to swap them into what we're going to define as our CAS space? Okay, so we'll start here. Okay, orbital 15 looks like this. It's kind of funky. It's a sigma-like orbital. This is basically the reverse of that thing. Okay, what is this besides a sandwich? Okay, this is a pi bonding orbital. This is the completely symmetric, or as symmetric as you get, pi bonding orbital. So no nodes besides the plane of the molecule. So we note that that is at orbital 17. Okay, so when I'm doing this, I'll have a note. I have a piece of paper or a notebook out, and I write orbital 15 sigma like, orbital 16 sigma like, orbital 17. Okay, this is pi like. So I need to note that. That's important now, right? Because we know we want to put that into our CAS space. Orbital 17 is not one of the 3 highest occupied molecular orbitals. And does everyone, if you don't know, does everyone pretty clear as to why this is a pi-like orbital?
Not there.
Okay. Does anyone want to explain to Ellery, how did you know that that was a pi-like orbit?
Because I guess the non-hybridized pi, so all the others hybridized sigma pi is going to be like between, but this pi is going to be perpendicular to the plane of benzene. That's where the pi orbitals are going to lie. And so the first bonding one is going to be where like all of the.
Why don't you draw it on the chalkboard? What do you mean? Because I think that will.
Or like each individual 6.
Yeah, draw the 6 carbons and their p orbitals. Probably more chalks. Which one right here?
Trying to draw this like out.
Very artistic. Better than I would have done. Okay, so explain what you're drawing now.
So these are going to be the p, I guess like the
Yeah.
p orbitals of each individual carbon.
Yeah. So these are the basis functions for our molecular orbital, our pi type molecular orbitals.
And so when they combine molecular orbitals, you have 6 of these. So there's, there are going to be 6 molecular orbitals. And so you can start by like, the first one is going to be the lowest energy, which is going to be when like all of these are say plus on top. So they can all combine. That's what that kind of looks like.
So your molecular orbital is taking all the ones on top and making like an upper orbital, and all the ones on bottom and making the bottom orbital. And they're not like the ones before that were all chunked into pieces.
Right, they have this same type of symmetry as these pi orbitals, where they are split by the plane of the molecule.
They're, the top and bottom are separate orbitals.
Yes.
Yeah, just
If this is all just one orbital.
Good point.
Okay.
so like this is one orbital with the.
This is one atomic
middle
orbital.
between. Should I do like the next one will look like?
Yeah, what would the next one look like?
Well, the next one's going to be like with the least amount of like competing. I guess.
It's called
Are you
nodes.
competing with this or competing with what?
No, so go ahead and draw it.
I think this is.
Yeah, good. So good. So
There's like a node here, there's a node here, because these can no longer overlap nicely there. There's going to be nodes, so it'll kind of look like say like red on top, and then green, and then red, and then green on the bottom.
good. Thank you. Good. So you'll see that as you increase the number of nodes, the separation between plus and minus, this is denoted here by some sort of binary thing, then you increase the amount of energy. So, for example, what would the highest pi star orbital look like for benzene? Yeah.
Every other orbital is going to be a node between.
Right. So in that case, so for the highest one, you're going to have plus minus, minus plus, plus minus, so on and so forth.
By looking at the models of the electrons, you can tell that it is only a pi orbital since all the hydrogens are, like there's no dependence over the hydrogen-carbon bonds, the carbon-hydrogen bonds. So there's no like sp character, there's no like s character, it's just the pi.
Right. Yep. Good. Very good. Okay, so we've noted that orbital 17 is a pi orbital, and we are going to want to include that in our active space. So that's noted somewhere, right? Now we keep going. 18. Does this look pi-like? Greg? Why not?
Because they're not, the way I still think of pi and sigma is from Gen Chem, where pi's can rotate and sigmas can't.
Okay.
So to me, I can't visualize a way where this can rotate without any central. So that's my reason.
Okay. I don't know what, I think, well, anyways. How I would describe it is that there is no node in the plane of the molecule, and we can see from the constituent atomic orbitals that there must be a node in the plane of the molecule for it to be pi-like. And there is no node here, right? This is the plane of the molecule, and there's no node there. There are nodes here, but no node in the plane of the molecule.
Yeah, okay, yeah.
Okay? Okay, what about this one? Is this pi or sigma-like? Sigma, right? Same reasoning. I would use the same reasoning. Okay. So this is orbital 19, which is one of our highest energy occupied molecular orbitals, one of our 3 highest energy molecular orbitals. So this is one that we want to be pi-like in our CAS space. Is everyone reasonably okay with what I mean by that? So now we note 19 sigma-like, right? Little notes. So we're going to have to swap which 2 orbitals? Yes, Troy.
19, I think it was 17.
Yes, okay, so we're going to do a swap between 19 and 17. Okay, so we'll write that down as you're going through this orbital, these orbitals, okay? Okay, so here is Ellery's, basically what Ellery drew up there, right? This is our second lowest energy pi bonding orbital. There's a node in the plane of the molecule, and then there's a node in the center of the molecule separating exactly like separating those 2 lobes or 4 lobes of the orbital. And then we have another variant on that same theme, which is our third lowest energy pi bonding orbital. Okay, any questions so far? All right, so that's the occupied version. All we have to do in the occupied orbitals is swap 19 and 17. Yes?
What would be the picture for that one? Like the drawn out one?
Same thing.
It's just the opposite, like.
It's just moved around, basically.
Now,
Yeah. What?
how come there wasn't one for that, like the lowest one? How come there wasn't one where all the charges are on the bottom?
Oh, how many ways can you do that? And how many ways can you do this one? I mean, so could
You
you?
only move, because if you move one, you have to move the other to see the opposite of that one.
So go up there and try to draw how many variations on one node in the center of the molecule can you draw? Like one node perpendicular to the plane of the molecule. So how many ways could I do that? I have the negatives over here in this case and the positives over here on the top. I can draw.
It's just visible.
Yeah. Okay, now let's look at the anti-bonding case. Okay, what is this? What about this? Greg, is this pi or sigma-like? Good. Okay, so 22 is our lowest unoccupied molecular orbital, is pi-like, so it is a pi star. That's fine. That should be in our active space. What about this one? Okay, good. What about this one?
Sigma-like.
Good. Sigma-like.
On National Donut Day.
Yeah. Yeah, okay, so now we know 24, sigma-like, that's not what we want. Okay, what about this one?
This one looks sigma-like.
Yep, good.
I just have a question.
Yeah,
Why is it reminds me of the colored yellow boxes?
that's just where the 0 of energy is. I don't really understand that myself, to be honest. I was asking Tony about that earlier. What about this one? Good. This one? So it's sigma star, but yeah, sigma-like. Yeah, sigma-like. This one's funny. But sigma or pi-like. Good. What about this one? Good. So this is the completely alternating one, right? As many nodes as you can possibly make. This is the last pi star orbital, so we could stop looking at orbitals at this point, right? And we say, okay, now which ones do we need to swap in the antibonding case? So clearly we want 30 in our active space, right? Does that everyone understand that? Which one do we remember if we're taking notes?
23.
So we want 20. So 22 is our lowest unoccupied molecular orbital, and then 23 and 24 are also. And 24, if we remember, was sigma-like, and here is our final pi star state. Okay, so we need to swap 24 and 30. Okay. So now we're going to quick Gauss U, and we're going to look at how to do that. So just so we're clear, I already knew that 30 was pi star state, right? But if you got to whatever you put as your final add list here, and you hadn't found all of your pi star states, you would have to add more. So when you're doing naphthalene and anthracene, you're likely going to have to go pretty high up there to figure out where the final pi star. This is a very high energy orbital, right? There's a lot of nodes in there. Okay. Oh, that again. Okay, so let's take a quick peek at this CAS-SCF calculation input file we made. So this is what it looks like. This is for benzene. Remember, the geometry in here is not the optimized geometry. Hey Rex, could you hit one of those lights? It's kind of hard to see the screen. I think it's the far left, or yeah, it's better-ish. Okay. So this is not the optimized geometry. Additionally, we have a wave function in our checkpoint file that we can read in as our guess. And we want to read in as our guess because we just look through all of the orbitals, and we know in this wave, when we computed the wave function using the optimized geometry, B3-lip, those are the orbitals we got, and we want to tell it, here are our guess orbitals, but swap these around and make this our active space. Okay, that's what we want to tell it. So we have to make a little bit more complicated input file than this. And that's why I gave you these files to work with. And what you're going to do when you do your project is just take these and alter them to accommodate the naphthalene and anthracene. Okay, and it's going to be relatively easy, and I'll walk you through how to do it. Okay, so we're going to look at benzene CAS-SCF enroute1.com, which is in that benzene file if you want to look at it along with me. And you're going to see a little bit different Gaussian input file than we've looked at before. There are actually two runs in this single file, separated by this link 1 line in the middle, if I could highlight it here. Okay, this separates two different jobs, basically. So it's as if you ran a Hartree-Fock calculation followed by a MP2 calculation or something like that. Okay. But in this case, what we're doing is a CAS-SCF calculation in the first one. Guess is basically reading in our orbitals or wave function. So guess is just saying how are we going to guess what our initial orbitals look like. In this case, we're telling it to read from the checkpoint file. This is the checkpoint file, and I'll show you what we're going to do for that in a second. But we're going to read it and we're going to alter it. And that's what this job is going to do. And you can sort of ignore the, oh, and the geometry, since you notice I haven't yet defined the geometry, but that's because I'm actually just going to read the geometry directly from the checkpoint file too, because I have that in there as well. And that's the optimized DFT geometry, and I'm going to read it from the checkpoint file. And this other stuff is just computational specific stuff. Okay, then we have our title card. We have our charge and spin, or declaration. And then we have these two lines, 17 and 19, 24 and 30. So what are these? Yeah.
The orbitals that we're switching.
Yes.
to-
Good. Good. So we remember we said we wanted to switch 17 and 19 and 24 and 30. So that's as simple as that. That's how we dictate that we swap those things. And all of basically this entire thing right here, all that does is read in geometry and orbitals from the checkpoint file, and then swap those two orbitals and print out a new wave function, basically. It optimizes it, but whatever. Then we're going to run an actual CAS-SCF calculation for root 1. And we're reading it in from the swaps version of this thing. And the geometry is being read in from there as well. Okay, any questions on that? You run this job exactly the same as you would run. You ran your DFT geometry optimizations. Just G0, you put it in that. You can either run it directly on your computers if you have Gaussian installed, or you can run it on the cluster using a submit script, just like we ran before. Okay. So if I run that, I will get output files, my log output file, highlighted here, and my checkpoint file here. Oh, one quick thing before. So remember, it's going to read the initial wave function and coordinates from this checkpoint file. Okay, we haven't created that checkpoint file yet. So what I'm going to do is I'm going to just copy my DFT checkpoint file to that name. It will then read initially the DFT wave function, orbitals and stuff, and geometry, swap them, and overwrite that checkpoint file. Okay, so that's as simple as taking my DFT checkpoint file, which is right here. I'm going to copy it to this guy. And this is before only, it has to happen, you have to do that before you run that job, okay? And I hit return. I'm not going to do it now because I've already, yes?
And then the optimization with DFT would be just for the ground state.
Yeah, that only optimizes the ground state. That's the file that we just viewed and determined where all the orbitals were, right? So it performed that optimization, both the geometry and an orbital and a wave function optimization at each geometry step, right? We looked at only the optimized geometry and the optimized orbitals of that optimized geometry. And then we determined that 17 and 19 needed to be swapped, and 24 and 30 needed to be swapped in order to get the right active space that we want. Yes?
So it looks like we're doing a couple of these like end routes. We're probably have to do that each time, right? And copying the checkpoint file that's made.
For every time you run this CAS calculation, you have to, yes, make a new checkpoint file from your DFT checkpoint file. So you want to keep that DFT checkpoint file sitting around. You don't want to overwrite that. You want to keep that sitting around. That's going to be your sort of, that is your basis set, basically, for your CAS calculation.
You only have to run the DFT once.
Correct. So now I'm going to run 3 routes. You can see I have 3 files here. I want to run 3 routes of this CAS66. So I'm going to create this 3 additional copies of this DFT checkpoint file. So for example, CAS-SCF 66 enroute1.check, enroute2.check, and enroute3.check. Okay. I'm not going to do it because then when the Gaussian calculation runs, this checkpoint file will be overwritten with the new orbitals. And we're going to view that in a second. But let me just, before I do that, let me show you what the en route 2 input file looks like. Doesn't look terribly different from the en route 1. Just en route 2 is importantly is in this line. And additionally, you must rename your checkpoint files to be the en route 2 variety or version. Okay, any questions on that?
So what did we get from the no root cast SCF?
It would default en route 1.
Oh, okay. Because ours is the file name that didn't have a root specification.
Yeah, it defaults to en route equal to 1 for the ground state. Okay, so I actually like to look at the log file, text log file, and you're going to see actually if you actually look through all of this, which we're not going to, but you'll see 2 initiations of Gaussian because there's that link thing that separates 2 different jobs. So Gaussian has been run twice, and the output of it dumped into this log file. The first one we don't really care about. All it's doing is swapping the orbitals, basically. The second one, so all I did now is go down to the very bottom of the file, is what we are interested in. And it prints out all of this. This is basically a humongous summary of what it did and what it determined. The important thing here is state 1A, Hartree-Fock equals negative 230.7382219. That is the energy of whatever root that you were looking at. Okay, so that's the energy of this state. And I'm looking at the en route 1, so this is the ground state CAS SCF energy. Okay, you can also look at things. So you can look at these things. These are, and we can also look at them in Gauss view, but this is representations of each of my orbitals and their populations. And if I go up to the top, we should start to see, okay, here we go. So we see eigenvalues 11, 12, 13, 14, 15 is 2, right? So if this is, that's representative of the population of that orbital. And if we go, does anyone remember what the highest occupied molecular orbital number was in the previous one? 21, right? Something like that. Okay, so now if we look at orbital 21, and actually if you looked at orbitals in the CAS space 19, 20, 21, you should see non-integer, potentially, eigenvalues. Do you see that? So for 18 is not in our CAS space. So its occupancy is dictated to be 2. Does everyone understand that? Because I haven't allowed electrons to be excited out of it. My active space was 6, so my active space was 6, 6, and I dictated which orbitals those. It automatically knows which orbitals those are. Those are the, once I've done the swapping, of course, that those are the top, the 3 occupied, the highest 3 occupied, and the lowest 3 unoccupied. That's how it defaults to. Okay, so it does not allow excitations out of orbital 18, only orbitals 19, 20, and 21. And we can see non-integer values of the occupancy in 19, 20, and 21. Why is that? Yeah.
Those are the ones that are getting excited.
And so what that means is actually even in this ground state, which we kind of somewhat naively think should be strictly occupancy of 2 in the pi states, there is some contribution from the pi star states. Okay, so this is truly a multi-reference method. Okay, so what I do is I take this Hartree-Fock energy, and that's going to be the energy of this state. And I'm going to put it in a file called stateenergies.dat, okay? So you see this negative 230, blah, blah, blah. I've put in state 1, negative 230.7382219. Okay? You can do that however you want. You can put it in an Excel sheet, you can put it in, write it down, however you want. I put it in that file. Then we do the same thing for en route 2 and en route 3. And then we throw a wrench into the works and we realize that actually, when we look at these things, we are dictating that the spin state be what in this case? Singlet. Now, remember from the helium case, that's not necessarily going to be the situation. When I excite an electron, in the ground state, certainly they're all doubly occupied. That's clearly a singlet. But we're not necessarily going to have a singlet be our lowest line excited state. This calculation here is only going to do singlet roots of this wave function, not triplet roots of the wave function. So we, in addition to doing these 3 singlet roots, we're going to do 3 triplet roots as well. And actually the third one doesn't converge. I haven't figured out why yet. And then we're going to look at which of those, and then you have to compare the energies of those different things to see which have the lowest lying excited states. So I've already done that, and actually I have it in PowerPoint as well. If you do that, you'll get a table that looks something like this. State 1 is our ground state. It's the singlet. It has the energy that we just looked at, -233.7. Turns out, if you do those calculations, the triplet is the next lowest lying state. So the first excited state is actually a triplet. This is in actually very good agreement, and then we get a excitation energy, which is a vertical excitation energy of 3.82 electron volts. Okay, so which is simply the difference between these 2 numbers, which will be in Hartree, and then converted to electron volts. Everyone clear on that? So just making this the zero of energy. This is the vertical excitation. In very good agreement with the experiment. It has been characterized for a long time as a triplet state. The next lowest energy state is a singlet. That has vertical excitation energy from my calculations of 4.97 electron volts. Also in pretty good agreement with the experiment of 4.89. Now, after that, I found that it was a triplet state. What's the next excited state? I couldn't, in my about 15 minutes of doing literature search, could not find a paper that had this energy. The next energy I found was for a singlet state at 6.18. So there are actually a number of possible reasons to have discrepancies for this. In particular, especially when you start to get to higher lying excited states, my calculations are going to have issues, or our calculations. Does anyone know why?
Worry about vibration. Is that not a thing?
So this is strictly excited state. So you actually have to worry both about. So this is electronic excited state. So we don't really have to worry about vibrational states. But I should also mention there's also an issue with the experiment because we are strictly calculating vertical excitation energies. The experiment actually can be challenging to measure strictly vertical excitation energies. So you excite to an electronic state given the ground state geometry. That's what a vertical excitation energy is. But if the lifetime of that excited state, if it's greater than 0, it's going to evolve for some time on the excited state potential energy surface. The geometry that is the optimal geometry in the excited state is not necessarily the optimal geometry in the ground state. And so it could move away from that. And typically that means it's falling down in energy. And then it might release energy. So that might be what the experiment is calculating. It's actually not the vertical excitation energy, but the energy difference between more relaxed excited state geometry and the ground state geometry. So that's possibility in the experiment because it depends how time resolved their experiment is. It's very, very fast, then it's probably close to vertical excitation, but no. But we also have to worry about our calculation in this in this case, when we get to, although I actually would think that this state should be reasonably well described, but beyond that, I would start to worry. Because our active space is reasonably small. Okay, so we are only looking at excitations between the pi and the pi star. We don't allow sigma electrons to come out, and we don't allow pi electrons to go into higher than pi star orbitals. So so there could be some crazy stuff happening in the excited state situation that actually makes those lower in energy than this state, or makes this actually an unrealistic state, for example. So you would have, in order to determine if that were the case, you would have to increase your cast space and rerun the calculation. Yes?
If we were to take that like 618 of the next excited state to be like relatively true, wouldn't that mean that the one like the value that we got to the fourth excited state be like a low ball of what it should be, because it should be decreasing every time. Like the spacing between each energy level should be decreasing, but the spacing between the third and fourth one is like 0.1 electron volt. So then the next one should be less than 0.1, but it's actually
yeah, this sort of at a certain limit that becomes true, but for a while that's not necessarily true. Additionally, I forgot one little caveat here is that I haven't done this since basically undergrad. Worried about this, but this could be a symmetry forbidden transition too. I haven't thought about that until just now, which means experiment wouldn't even see it, but we can still calculate what it is. So that could be another reason why they don't see it. Okay, so so that's it. We can look at the checkpoint files, but you guys can do that on your own. So why don't I just let you guys mess around with these and think about how to do naphthalene and anthracene. I think that's the most best use of time. Are there any other questions for me on either theory or how implementation of this method, or what you have to do now? Yes.
Is there a way to open gas view through the cluster?
No.
Okay.
Do you not have gas view on your?
I do gas view on my computer.
Oh, it's just transferring files back and forth?
Just a bunch of copy back and forth.
Yeah, it's a little bit annoying, but it's the best way we could do it. Actually, we don't have a license for Gauss view on Linux, so I couldn't even do it.
That's fine.
Yeah, it's a bit of a pain. But if you have Gaussian, do you have Gaussian installed on that computer? Oh, okay. Well, we could get it installed on that computer. Because although so even these benzene 6,6 root calculations, CAS-SEF calculations, I ran them on my desktop actually in my office. They only took a minute or two. So they're not computationally demanding. Now, when you go into naphthalene and anthracene, so naphthalene, where the pi space is 1010. Anthracene, I didn't tell you what it is. You have to figure it out. Remember these. The scaling of these is quite dramatic with the number of electrons and orbitals. So they do come significantly computationally more demanding. But on the cluster, it should be no problem. So I would take these input files. When you run them on the cluster, you can also change nproc shared. So this is how many processors you're using for this calculation. On the cluster, a single node has 20 processors, and you may as well use all of them because you're the only person running on it on a given node when you submit a job. So you will want to probably change that number to 20 or something higher than 3. Memory, there's 32 gigs of memory on each node on the cluster. So I would change %mem to greater than 4, especially. I didn't run into any issue with, I've done naphthalene, I haven't yet done anthracene. I ran into no issue with naphthalene with 4 gigs, but you may as well bump it up because the space is there. So is everyone clear on what they should be doing? So you're going to take these files, so I've created these and given you copies of all of these benzene files, and I would suggest just modifying these to perform the function on naphthalene and anthracene. what I would do is start by going into Gauss View and creating a DFT optimization job for naphthalene and anthracene. Run those jobs, obviously. And then modify these and point to and make copies of your naphthalene anthracene B3lib optimized checkpoint files. And don't call it benzene. Okay? Good.